Well, here it is, folks, our last section of our astronomy unit. This time around, we're going to be talking about some really big new ideas here, some of the things that are on the very cutting edge of what we know about the universe. So strap yourselves in. Energy. Don't forget to take notes on the red slides. You should have the notes handouts to go with this. And don't forget to look for the owl and summarize what you learned at the end. So the first thing we're going to talk about today is constellations. And you guys know some of the constellations. You've probably seen things like the Big Dipper up in the sky. And sometimes you might wonder, well, how the heck do they get those pictures and all that stuff from just those stars that are up in the sky? And it might be kind of hard to see that, and that's understandable. But I think there's two things to think about there. Number one is that back then, the sky was a lot darker because we didn't have all of these lights, street lights and house lights and city lights and things like that. So you could see a lot more stars. So it was a lot more detailed and easier to see these things. But secondly, I think probably more importantly is that they didn't have TVs, they didn't have radios, they didn't have phones and computers and all that modern technology that we have now that occupies our time. So what they would do a lot of times is just tell stories about things, and they would sit and look up at the night sky and try to create stories around what they saw up there. And I think that has a lot to do with where these constellations came from. It was just people using their imagination to make stories up about the universe and about religious ideas and things like that. So the first constellations that we have records of came from Mesopotamia, and it was around 1000 BC. So that would be about 3,000 years ago. And then they were later categorized and cataloged by somebody named Ptolemy, and that name should sound familiar. We talked about Ptolemy before, and he was the guy that first came up with the geocentric model of the universe, and we all know that that wasn't quite right, but he did do a lot of studying, and if you recall, he was one of the first guys to actually use scientific observation and take measurements and things like that. So he was a very early astronomer as far as real actual astronomy goes, and using science to do astronomy. So that was early constellations, but you might be wondering, well, is that all it is just pictures in the sky? Do we really need to know about these things? Are they really useful to us now? And the truth is that they are, because we've already had this system set up now for thousands of years. We basically have kept that system in place, and we use it to map out the sky. So you might hear things talked about in terms of what constellation they're in, like we talked about the Orion Nebula when we were talking about Edwin Hubble and his discoveries. And the Orion Nebula, well, it's called the Orion Nebula because it's in the constellation of Orion. So we still do use them to this day as sort of place markers in the sky to map out the sky and talk about other things that are in space. So, do you recognize this constellation? This is one of the easiest constellations for us to see in the sky. And it's supposed to kind of look like that. This is the constellation Orion, and right down in here, this is Orion's belt, and he's supposed to be holding up a shield over here, and he's kind of holding up a sword over here. This is his arms, and down here are his legs and things like that. This is supposed to be the sheath for his sword. So that's the constellation Orion. And again, I understand it seems like a bit of a stretch to see all those things in this picture, but again, remember that they were just kind of making up stories. It's kind of like when we look at a cloud and see something like a bunny rabbit in the cloud or something like that. Now, what's that guy right there? Well, we've talked about that guy a little bit. That is Betelgeuse, and that is a red supergiant. So as you guys know, that is a star that's getting near the end of its life, and so it actually could explode and become a supernova kind of at any time. But remember, stars last for billions and billions and billions of years. So the end of a star's life, that could mean that it could explode tomorrow, or it could explode 10,000 years from now. We really don't know, but we do know that it's towards the end of its life, mainly because of the color of the star. Interesting idea is that An interesting idea here is that this star actually could have exploded yesterday or a few years ago, because remember, it takes that light to some time to get to us, so it doesn't arrive here immediately. So it is actually completely possible that Betelgeuse could have already exploded, and we just haven't seen it yet because the light hasn't reached us yet. But we wouldn't know that for a little while. When it does happen, the prediction is that it would be so bright that it would be about the same brightness as the full moon, but we would be able to see that during the day as well as night. All right, so make sure you fill all that stuff out. Betelgeuse, Red Giant, and the constellation of Orion. That's one of the ones that I want you to be able to recognize. And here's another constellation that I'd like you to be able to recognize. So can you find it here? You've seen this one before, probably the Big Dipper. There it is. So interestingly, the Big Dipper is actually not technically a constellation, and that's kind of funny because I think it's probably the most well-known constellation out there, at least for those of us in North America. And it's actually part of a larger constellation that is the official constellation, and that constellation is called Ursa Major, and that means Big Bear. Ursa means bear, major means big, so it is Big Bear. And this sort of animation, well, not an animation, this drawing over here to the right is what it is supposed to look like. One of the things that I find very confusing about this is that part right there. I don't know about you, but I've never seen a bear that has a tail like that, and that's actually this part of the constellation here. So it's a pretty major part of that constellation, and they kind of made a point, I guess, to give it a tail, but I don't know. Bears don't have tails like that, so I'm not really sure where that came from. That's kind of weird to me. Now, another constellation that you might know about is the Little Dipper, and the Little Dipper is a lot harder to see in the sky than the Big Dipper, but there is a good way of trying to find it. If you can find the Big Dipper, which is pretty easy to see, it's probably the easiest constellation to see in the sky, and you take this star here and this star here, and you kind of draw a line going right through the both of them, kind of like that. It's going to point you right at the handle, the end of the handle of the Little Dipper. Now, that is part of that constellation, the Little Dipper, but it is also kind of an important star in itself, because this is the star that we call Polaris, which is also known as the North Star. So go ahead and label that picture. Make sure you put all of these different lines and words in here so that you know what all those things are. Now, right now is probably a good time to let you know that we will be completing any video questions that you have in this handout, in this homework handout. We'll be doing those in class, so you don't have to worry about those. All right, so first of all, let's talk about why the North Star is the North Star. Well, basically the idea is, if here is the Earth and here is the South Pole, and it goes straight through to the North Pole, and you can see that if you kind of keep going straight up along the axis of the Earth, the North Star is directly overhead. Now, we'll talk about this a little bit more in class. I don't want to get too much in detail about this right now, but the interesting thing is, because of that fact, because this lines right up with the North Pole, what that means is that we've seen how stars appear to move in the sky because of the spinning of the Earth. But the thing is that all of these stars out here are all going to look like they're kind of revolving around the sky like this. But the North Star, because it's directly above the North Pole, won't do that. The North Star basically stays put in the sky. It stays directly where it is. Now, an interesting thing about that is that the North Pole of the Earth has not always pointed at that particular star, Polaris, because the pole kind of wobbles a little bit. Think of a spinning top, and the way that the top part, the handle that you actually spin on the top, kind of wobbles as it's spinning. Well, the Earth does that too. So sometimes the North Pole is facing maybe over that direction, but it takes thousands of years for that to really change in a noticeable way. So for our lifetimes, this will always be the North Star, but For people thousands of years in the past, there was a different star, and for people thousands of years in the future, there will be a different star that the North Pole is pointing at. So, a couple of things that you can figure out by finding the North Star. One is kind of an obvious one. Once you find the North Star, whichever direction that is, whichever direction you have to look to see the North Star, well, guess what? That is north. So that's one thing you can find out about it. So when you're facing the North Star, you are facing north. But there's actually one more thing. And this is something we will, again, kind of practice in class a little bit. And this is kind of cool because this is one of those things that you can actually do at home. So basically, the angle from the horizon to the North Star is going to be equal to your latitude. Okay, so whatever that angle is, that will be your latitude. And I want to take you back to when we talked about latitude and longitude. And I want you to think about this. So remember, this is the equator on the Earth, right? And we talked about the idea that the North Pole is kind of like this. And a good way to remember that is that you know that that angle right there is a 90-degree angle. So that's 90 degrees. And remember that the North Pole points at the North Star. So if you are standing at the North Pole, you would have to look directly straight up in order to see the North Star. And so if you take that angle from the horizon to the North Star, you would get a 90-degree angle, right? So that angle right there from the horizon to the North Star actually is the same angle as your latitude, because at the North Pole you would be at 90 degrees north. All right, so now we need to start talking about some of the really big things in the universe. And one of the biggest things, one of the biggest groupings of things in the universe, as I've said before, the universe kind of clumps together in different shapes. And one of the things that makes it clump together is gravity. And so gravity, when it's clumping matter together in the universe, one of the biggest structures that forms out of that is these things called galaxies. And galaxies are large groups of stars, gas, and dust. And when we say large group of stars, what I mean is usually millions to hundreds of billions of stars. Most galaxies have over 100 billion stars, so that's 1,000 times a million times another 100. So I want you to take a look at this and just look at this simulation of how this works. What you're going to be looking at is basically a portion of the universe, right? The universe is everything, and you're going to see all this, what looks like kind of gas or dust or something like that. And that gas is really just, it's stars. It's billions and billions of stars. And I want you to just kind of see how they all gather together because of gravity. So this is the mirror for the Hubble telescope, and the Hubble telescope has really brought us some amazing images and some really major understanding about the distant parts of our universe and what goes on in those areas. One of the interesting things here to understand is that the Hubble telescope mirror, when they first put it up there, was actually off by a very tiny fraction of an inch. The curvature was just off by a tiny amount. So when they first brought back images, they were fuzzy. So after about 6 months or so, they actually had to go up and put a lens on it, which would be very similar to the idea of putting glasses on somebody. But So when we look up at the night sky, this is more or less what we can see. In a really good viewing area on a nice dark night, you can see somewhere around 2 or 3 thousand stars in the sky with the naked eye. So once we got the Hubble up and working, what we wanted to do, what scientists wanted to do, was see how far we could see. And so they took a picture of a small portion of the sky and really kind of magnified it and blew it up. And this is what they found. Some really cool looking stuff here. Some nebulas and different things that we see there. But you know, they weren't quite done yet. What they wanted to do next was they wanted to kind of point the Hubble telescope at a completely dark section of sky, a part that from the technology that we had at the time, basically we couldn't see anything at all in that part of the sky. And when we did that, we got so something that you may have noticed in looking at that picture there is that it seems like there's a lot of different kinds of galaxies, different shapes. And when I first showed you that animation of how galaxies form, you could see that they kind of swirl around a lot and they seem to kind of change over time. Well, that leads us to being able to classify a few different types of galaxies. So, the main types of galaxies, there's four main ones that you want to know. They can be spiral galaxies, and the Milky Way galaxy, our galaxy, is one of those spiral galaxies. That's the type of galaxy that our galaxy is. And that usually happens after a galaxy has had time to develop for a while. There are barred galaxies. A lot of times these ones look a lot like the spiral galaxy, but you can see that there's sort of this bar in the center. That's where the bar comes from right there. And those a lot of times happen when, believe it or not, when two galaxies collide with each other, this can happen. There are elliptical galaxies. These are usually fairly young galaxies that haven't really gotten a chance to form these shapes yet. And then there are irregular galaxies. And again, these can happen because of collisions with galaxies, or they can happen because the gravity of a nearby galaxy starts to kind of pull it into odd shapes. Those are the main types. So we are, if you try to find us sort of on a map of the Milky Way, and by the way, this is not a picture of the Milky Way galaxy, right? We don't have pictures of the Milky Way galaxy because we're in the Milky Way galaxy, and where we are in the Milky Way galaxy is somewhere right around here. We're on one of these sort of outer spiral arms of the Milky Way galaxy. That's kind of what it would look like from the side. We'd be out there. And this beautiful picture right here is what our Milky Way galaxy looks like from Earth. If you're looking at this, first of all, you can kind of see why they would call it a Milky Way. It's kind of this white kind of color here. And so this is kind of hard for us to see. We really have to get a good dark sky to see this. But if you ever go out into the woods or something like that, you can kind of see this a bit. And basically, when you're looking at this, you're looking in towards the center of our galaxy where all of those bright stars are. So speaking of the center of galaxies, what we see here is an animation on the left here and a picture of an actual galaxy on the right. And what we see is this central part here. Remember that galaxies are formed by gravity. It's gravity pulling all these stars together. And as they get closer and closer together, they start to swirl around this central area and get sucked into each other. And if you remember talking about black holes are basically the idea of a lot of matter crammed into a small space, which creates a lot of gravity. And so that's what's going on here. And this is a lot of matter. Remember, black holes can be created by one really big star. Well, this is millions and millions and millions of stars all crammed together. So these form what are called supermassive black holes. And we can actually see kind of this image on the right here, and in this box, that really basically is the area where a black hole is. And I want to say that's an area where the black hole is because you can't really see black holes, because remember, no light can escape from there, and that's how we see things, is by looking at light. So you can't really see a black hole, so that's not a picture of a black hole, but that's the area where a black hole is. So this type of thing here, this is found at the center of pretty much all galaxies, and this creates a very bright, hot area because there's so many stars crammed into this. So I want you to take a look at this next animation here, and this is basically what these things look like. So these really hot, bright centers of galaxies have a name. These are called quasars. And the name quasar comes from the term, it's sort of a shortening of the term quasi-stellar radio source. Quasi means sort of, it means kind of like. And so the reason why it has that name is because these were a source of a lot of radio energy, and we didn't really know what they were for a long time. So they kind of looked like really bright stars in the night sky. And so we said that they were kind of like stars, and they were giving off radio energy. And so that's what we called them. But now we know that they're actually the bright centers of distant galaxies. And these are caused by supermassive black holes, by all of these stars swirling together in the center of a galaxy. All right. Next thing that we need to talk about here are exoplanets. And exoplanets are planets that are orbiting other stars. You guys know that we orbit our sun, which is a star, but there's billions and billions and billions of stars out there. And so there are planets going around those guys too. And so this picture that you see here, this is an actual picture of an exoplanet. This is one of the first pictures that we found. Right inside that little box there, that little dot there, we actually have two exoplanets right there. Two planets going around this star right here. And that's one of the few actual pictures that we have of them, because they're a little hard to see because they're very far away. So you might wonder, well, how do we find these? We'll talk about this more in class, but basically the way that we find these is by the fact that a planet going around a star, well, when a planet is on this side of the star, it will pull the star a little bit in that direction. And when the planet is over here on this side, it'll pull the star a little bit in that direction. And when it's over here, it'll pull the star towards us a little bit. And when it's over here, it'll pull the star away from us a little bit. And so what that does is we can use that Doppler effect that we've talked about before. So as it's coming towards us, the light will be shifted towards the blue end of the spectrum, and as it's going away from us, the light will be shifted towards the red end of the spectrum. So what we see is that the star's light gets a little bit bluer and a little bit redder and a little bit bluer and a little bit redder over certain periods of time, and that can tell us that a planet is going around it. Another way is that as a planet orbits a star, if it goes in between us and a star and causes something that basically is like an eclipse, what that does is it cuts off a little bit of the light from that star. And you can see this is kind of a graph of the light of the star, and you can see it kind of dipping here. So as the planet goes around, when the planet's over here, we see the entire star in all its brightness. But as it moves and goes in between us and the star's light dips a little bit. It gets a little bit dimmer. And again, if we see that happening on a regular basis, like once every 6 months or once every 2 years or once every 10 years, then then we can understand that there's a planet going around it, we can really learn a lot from that period of how long it takes to go around. We can learn things like how far away the planet is from the star, how big the planet is, all sorts of different things. We can even try to see the light that is going through the atmosphere right here and try to find out what kind of things the atmosphere is made out of. So at this point in time, we have found, and actually this number is probably not correct anymore, we have found thousands of different exoplanets out there. So we've only begun this search. The first exoplanet was found in 1995, and that might seem like a long time ago to you, but remember, most of the stuff that we've been talking about here was discovered hundreds of years ago. So this is a very new science. A lot of the stuff that we've been talking about in this lesson here is very new science. So we're still discovering these, and we've gotten to a point now that we can kind of estimate how many stars have planets, and even more specifically, how many stars have Earth-like planets, planets that are kind of similar in size to Earth, and more importantly, planets that are in their habitable zone. And we found that it's probably something like 1 in 5 stars have Earth-sized planets. Now, here's an interesting thing. I want you to help me out with this math here. So 400 billion stars in our galaxy, and about 1 in 5 of those stars has Earth-like planets going around, and planets in the habitable zone. So if we divide that by 5, that's about 80 billion habitable planets just in our galaxy alone. And there are over 100 billion galaxies in the universe. So you got to take that 80 billion number, that's the number of habitable planets in our galaxy, and multiply that number by another 100 billion or so. And that gives us the total number of habitable planets in the universe. So, question is, do you think aliens exist? Well, based on those numbers and based on the fact that life happened here on Earth pretty quickly once the Earth formed, and plus the fact that life's been wiped out quite a few times on this planet and has come back strong, it seems like when life has a chance to happen, it happens. And so with all of those habitable planets out there, it seems to me like a pretty good possibility just based on those odds that there could be alien life out there. Now, you guys know about the Big Bang Theory, but there's a couple more details that we left out. So there's basically 3 possibilities here once we understand that the expansion of the universe is something that is happening. So we could get an infinitely expanding universe like what we see here. The universe just keeps getting bigger and bigger and bigger forever. Or our second possibility is that the universe could get bigger to a point, and then gravity could kind of all pull it back in to itself, and we could go back to this thing that we started with, which is called a singularity, which is all of time and space itself kind of wrapped up in one little point. And maybe we could get another Big Bang again, and then another Big Crunch again, another Big Bang again, and maybe we're just in the midst of a series of Big Bangs here, and we're just in one of them. And the third possibility is that it could expand to a certain point and then just kind of stay where it is. Maybe the expansion of the universe slows down and gravity kind of ends up balancing it out, and it just comes to a stopping point. So those are the 3 possible ideas here. It could keep going, it could shrink back down, or it could just grow for a while and stop. But in all of these cases, what we would expect, because there's, you may have heard of Newton's law of motion that says an object in motion stays in motion. Well, there's a little bit more to that, and that is an object in motion stays in motion, and that it goes at a constant speed and in a straight line unless acted on by a force. Now, what that basically means is that things don't speed up or slow down all by themselves. There has to be some sort of force. A lot of times on Earth, that force is friction, or if you push on something, or if you step on the gas pedal in a car, or make the pedals go on your bicycle. Those are all forces, and those can make you change your speed. Well, in the universe, we wouldn't expect there to be any forces like that are kind of pushing on anything. There is gravity that can make it slow down. But here's the thing. When we actually look at the data and look at how fast the universe is expanding, what we see is that the universe is actually speeding up. It's actually accelerating as it expands. So in order for the universe to be speeding up as it expands, there has to be some sort of force happening on it. And the truth is, we don't really know much about what that force is. There has to be some sort of energy that's sort of creating an outward pressure. It's kind of thought of as being something like the opposite of gravity. Gravity pulls things together. This force seems to be pushing the entire universe apart. So we don't know much about this, and so we call it dark energy. This is a hypothetical form of energy that exerts an outward pressure, causing the expansion of the universe to accelerate. Now, another term that is a lot of times linked with dark energy is dark matter. This is another thing that we don't know a lot about. The thing is that when we look out in the universe, basically we can measure the gravity, the amount of gravity that's out there based on the motion of objects in the universe. And what we find is that there's way more gravity than there should be based on how much stuff there is out there. So again, we don't really know where that gravity is coming from, but we can measure it. We know it's there, and generally speaking, as far as we know, it is matter that causes gravity. So there's some sort of matter out there that takes up a large portion of the universe that we can't see, we can't feel it in any way, we can't observe it, we can't really interact with it. The only thing we can do is watch regular matter and see how it moves and measure the amount of gravity. And by doing that, we see that there's more gravity than there should be, so it seems like there's more matter out there than the matter that we can see. And we call that matter dark matter, the hypothetical form of matter that cannot be directly observed. Now, I said it couldn't be directly observed, but this is a really interesting picture. This is like one of my favorite pictures ever. Let me explain why. If you look at this and you see these little, what look like sort of stretched out, blurred image here, okay? I want you to think of the idea of if you put like a glass over something, or a magnifying glass, or the glasses that you wear, and what happens to that? It kind of creates something like this, where you see little stretched out images around the edges. So what this is an image of is actually gravity stretching out light and distorting the light. We'll talk more about this in class, but this is what's called gravitational lensing. And this is a direct effect of this dark matter. So gravitational lensing kind of looks something like this, where gravity bends space, like in this picture here. And this is where the star actually is, and its light gets kind of bent as it goes around this bent space and reaches us. Now, we assume that light moves in a straight line, so we kind of see the star over here when it's really over here. And this is kind of a very interesting thing. So all of this dark matter in here, we can look at a galaxy that's behind it, and sometimes what we see is we'll actually see the galaxy over here, and we'll see it over here too, and we can actually see that it's the same galaxy in two places in space because the light is getting bent by the dark matter, just like looking at something through a glass of water or something like that. So what we find when we look out into the universe and make all these measurements is that dark energy and dark matter make up almost the entire universe. It's only maybe about 4% of the universe is stuff that we actually know something about. And so that's pretty exciting for astronomers. That means that most of the universe is kind of completely unknown to us. We really don't know much about it. We just see the signs that it's there. So that leaves us with a lot of stuff to explore. So just remember that it's called dark matter and dark energy. Those words dark are there mainly because we can't really observe them and we don't know anything about them. Probably in the future we may give them a new name once we learn more about them, or maybe we'll just keep that name. But for now, it's just something that we have some indirect observations about. We don't really know much about. All right, well, that's it for astronomy now. So we learned about constellations and that they were used to tell stories, but now today they're also used to map out the sky. We learned about a few different constellations that I want you to be familiar with. We learned about Orion, Ursa Major, which includes the Big Dipper, and that's the Big Bear, and Ursa Minor, which includes the Little Dipper. We learned about North Star navigation and how that tells you which direction you're going. If you're looking at the North Star, you're going north. It also tells you your latitude. We learned about galaxies and how they are billions of stars grouped together by their gravity. We learned about a few different types of galaxies, and the galaxy that we are in is a spiral galaxy called the Milky Way. We learned about these crazy quasars, which are bright centers of galaxies caused by supermassive black holes. We learned about dark matter and dark energy, which is some of the more kind of perplexing and very misunderstood and something we just don't really know much about. And that there is more gravity than there should be. The universe is accelerating as it expands, and we just don't know what the heck that stuff is. So we'll talk all about this week in class, and I'll see you then.